Hello everyone, and welcome to the Easing Symphony AnimationSpec in detail. My name is Nicole Terc, and for those who don't know me, I am an Android GDE and also an Android developer at HubSpot. And you can find this and even more ramblings on my GitHub profile right there. Cool. But with this out of the way, let's take a look at what are we actually going to be doing today. If the name didn't already give it away, we're going to be over 3 things. We're going to be talking about animations, we're going to be talking about AnimationSpec, and we're going to be talking about easing. And in order to tie them all together, we're going to be making some music visualizers. Cue to see if it works. It works, great. But before we start with any of this, let's take a look at some basics. And in order to start with the basics, let's ask the most basic question of them all, which is, what is actually an animation? An easy way to define an animation is that it is the sequential change of a UI property, which basically means that given a UI property change, like a ball moving from one point to the screen to the other, instead of changing it right away, if you change it little by little in a sequence, you're going to end up with an animation. Cool. But now that we know what an animation is, our next question is, of course, what do we need in order to make an animation? And since an animation is a sequential change of a UI property, of course, the most basic thing that you need is a UI property that changes, right? Simple things. Now, since we're going to be making music visualizers, of course, these UI properties are going to be coming from music, right? But how do we get UI properties from music? Let's take a look at that now, and let's talk about music. So, UI properties. In order to get some UI properties from anything, be it music, be it images, be it whatever, the strategy is actually pretty straightforward. You only need to grab some properties, regular ones, not UI ones. Like in the case of music, we can get waveform, which is kind of like the sound blueprint. We can get amplitude, which is the loudness of the sound, and we can grab frequency, which is the pitch, and then just represent them visually. In a graph, of course. Everybody loves graphs, right? Cool. But now that we have UI properties in place, how do we actually animate these things? When we're talking about music, the usual strategy is to grab the sound, split it into frames, and then animate the change between each of these frames. So we can grab, for example, the average amplitude from one to another and animate that change, or grab the distribution of the frequencies in one frame to the next. And that's how you're going to get the UI change you need in order to make animations. Great. So far, so good, right? But now that we know how we're going to be animating music, we need something to actually grab that music and get these properties from it, right? So let's start seeing some code, and let's build ourselves a music reader. I'm going to be working with KMP, so I'm going to give a solution for using Android, iOS, and desktop. Now, again, since it's KMP, the easiest strategy to provide these sort of platform-specific things is to start with an interface, which in the case of our music reader is going to look like this. We're going to basically have an interface that is going to expose the waveform, amplitude, and frequencies for our music, and it's also going to have some helper functions that are going to help us load the file, play the file, and stop it. Nice. Now that we have this interface, the next step is, of course, create an expect function that is going to provide this music reader, and after that, for each of the platforms we are going to support, we just need to provide a specific actual function for the music reader. I'm not going to go super deep into how I created each of the music readers, but just for you to know, for the Android music reader, I am using Media Player and Media Extractor. For the iOS one, I'm using AV Audio Player, and for the desktop one, I'm using Clip. Don't worry, if you're curious, you're going to have the repository of all the coding here at the end of the presentation, so you're free to take a look at that. It's a bit dirty, but ignore that. But cool. Now that we have our music reader, let's start making some fun, right? I promised some music visualizers. So let's start with a simple visualizer for our music reader. In order to start this thing, of course, we're going to start our composable, which is going to be a music reader visualizer. We're going to start listening to this visualizer. We're going to start listening to the changes of these properties. And after that, Prophet, we're going to animate them, right? This is where tip number 1 comes in. Whenever I find myself with some UI properties that are already changing sequentially, which by definition music changes sequentially, I hope, an easy way to start understanding how these properties are going to change or how they're changing is to actually, instead of confusing myself with APIs, confusing myself on how to do this, is just to create a simple canvas. For those who don't know, I hope everybody knows, but Canvas is basically a composable that is going to let you draw things directly in the screen. So you can draw points, lines, bars, whatever. So let's do that for our simple visualizer. And in order to do it, we're just basically going to grab each of the properties. And let's say for waveform, we're going to create some points connected with a line. For amplitude, we're just going to draw a circle that changes in size. And for frequencies, we're going to draw the classic bars. Cool. Now that we have our tree canvas in tow, we can basically run this and nothing happens. But that is, of course, obvious because we actually haven't done anything about music, right? We have no music here. So important tip, don't forget this, and it should be obvious, but before starting with music visualizers, you actually need to get some music. You can use your favorite source, you can do whatever. In my case, I just asked my cool little brother for something, and he provided. So once you have your favorite music, you basically just add it into your project, and after that, you just load it up into your music reader, and voila! There you go. Some basic simple visualizer by just using Canvas. I hope everybody can hear that. I do, I hope. Cool. But with this out of the way, I think we're done with simple visualizers. Let's go to something more chunky. Let's create more visualizers. And when I talk about more visualizers, I'm of course talking about more animations. And when I talk about more animations, I'm of course referring to using some animation APIs. Which is always, there are a lot of them. They can be a bit daunting, but don't worry. The only thing you need to do is follow our trusty flowchart and identify which of the animation APIs we're going to use. Which in my case, since I'm going to be using a simple visualizer, is going to be animate as a state. Great. Now that we have our animation API that we're going to use, let's start with a basic animation. And the first step in any animation is actually to define which UI property we're going to change, right? Because that's the basic thing that we need. So let's take a look at our music reader, and just because I want to, let's use amplitude. You know, it's a simple level of the tree, it's just a float instead of float array. So let's create a basic animation using amplitude. And in order to start it, it can start like this. It can be a simple composable, where I'm going to be listening to the amplitude changes, and using this amplitude, I'm just going to paste it in our box that is basically a ball, which is just a circle. And how this amplitude is going to be changing, I'm going to be just changing the translation Y, which is a fancy way of saying that my ball is going to be going up and down as this amplitude changes. And since I want it to be an animation, not just a change, we just need to grab this translation in my animate float as a state and consume it as if it was a simple float. Whew, I talk too much and too fast. So anyway, this is all the code you need, and literally just copy-paste it with some omissions. But if you run this thing, you get a basic animation. Cool. But I think that's it with the basics. Now that we have something running, let's have some fun. And by having some fun, I of course mean customizing this animation. But how do we actually go around customizing animations? How do we start? Don't worry, the process is also fairly simple. And that is, given an animation, which again is a UI property that changes sequentially, you are just going to change how this UI property changes. So even if the initial state and the end state are the same, changing how this animation is going to change, you're going to have wildly different animations. Cool. But just to give names to what I'm saying here, whenever I refer to how a UI property changes, this is referring to how an animation plays out, and this is basically already talking about AnimationSpec. So let's jump into our customization number 1, which is AnimationSpec. AnimationSpec is an optional parameter in most of these animation APIs, and basically how you set it is basically you just set an animation spec. But what is AnimationSpec? If you take a look at the documentation, you're going to find something like this. AnimationSpec is the one that stores the specification of animation, including 1, the data type to be animated, and 2, the animation configuration. If you try to understand this definition, you can go at point 1 is pretty obvious. It's just basically whatever you're animating, a float, a color, whatever you want. But when we go to point number 2, what the hell is an animation configuration? What does it mean? Now, whenever I find myself in this situation where I'm not fully understanding what this documentation means, I usually just go to the source. And by that, I mean I just come and click into it and see how the code looks like. So let's do that right now. And if you do the AnimationSpec, you're going to find something like this. you're going to find that AnimationSpec is nothing else than an interface that has just one function that is called vectorize, that is going to provide the vectorized AnimationSpec. Great. We now know that AnimationSpec works with vectors, but this is still not telling me anything about this animation configuration, right? So let's go one step further, and let's just command-click into vectorize AnimationSpec. And if you do, you're going to find this. You're going to find that this vectorized AnimationSpec is another interface that is going to have some functions and some values. First, it's going to have a value that is going to define if this animation is infinite or not. Then it's going to have a function that is going to provide you the value of the specific animation given a time. Then one that gives you the velocity, sure. And last but not least, has one function that is going to give you how long this animation is going to be played for. Nice. I think with this, we can go back again to our definition and update it a little bit. We can change it and say that AnimationSpec is going to contain the data type to be animated, and also it's going to have information about the value, speed, and duration at a given point in its life cycle. A bit better, but let's take a look at how we actually use this AnimationSpec, right? If we go back to our customization AnimationSpec visualizer, the only thing we need to do is, inside this AnimationSpec property, we're going to create one. And don't worry, even if I am showing big words like vector and formulas and times and whatnot, you don't need to worry about that most of the time, because there are a lot of animation specs out of the box. Just to name some, we have things like spring that are going to mimic a spring. We have tween, which is kind of like the straightforward animation that is just time-based and is just going to move the value. And we have keyframes, one of my favorite ones, which is going to let you define keyframes in your animation that you want this animation to touch. So once we have this information, we can just go back to our AnimationSpec animation, and we're just going to be basically creating our own. We can create a spring, we can create a tween, or we can create some keyframes. And that's it. We're basically just changing one liner in these things, and by running it, you can get totally different animations. Nice. This is looking better. This is great, but this is still looking kind of boring. So let's take a little detour and let's do a bonus cooler AnimationSpec visualizer. And for this, let's just do a classic. Let's do a trail AnimationSpec visualizer. And by this, I mean those animations where you have one lead in animation and then you have other copies following behind. So just for the funsies, let's just create this. Going back to the code, the only thing you need to do is, instead of just observing your amplitude directly, you're going to actually create another float array, which is going to have your save amplitude, naming is hard, and inside of here, you're going to basically define how many of these copies plus the leading item you want. Now that you have this, you need to basically, whenever the amplitude changes, you're going to be rotating the values inside this float array, and of course, instead of just animating just one amplitude, you're going to go over this float array and create one for each. And that's it. That's all the changes you need. So once that we run this, you have your trail animation visualizer. But again, I am not one for like just staying with this thing, so we can just do it better. And instead of like making it a row, we can remove it to have one in front of the other. But since this is looking a bit confusing, let's just change the sizes too. Cool. That's better. But I think I'm going to stop for now in animation specs. In order to customize this even further, let's go to customization number 2, easing. Now, if you have ever touched animations and tween, you may have heard this word before. But what is actually easing? Easing, which is part of AnimationSpec, if you go into documentation, you're going to find a definition like this. Easing is a function that represents the animation fraction in time-based animation specs. Important notice here is not available for physics basic like spring, it's only time basic like keyframes and tween. Anyway, now this is just fancy words to like saying in another way of this is a function that is going to represent the progress of the animation at any given point in its life cycle. Still a lot of words, but basically this is going to be used to like speed up or speed down an animation. Still only words. So for the sake of making it more visual, let's see an example. In this case, I have the same animation in all of these 4 items in here. Is basically just a ball going up and down, and all of them have the same duration, believe me. The only thing that I changed is which easing I was using. As you can see in that purple line, as it goes up and down, is basically the time this animation has been playing. If you use a linear easing, this is going to match 1 by 1. But if you change the speed on how this thing moves, you're going to see that you can basically make this animation advance 90% of the progress in the first 10% of the time and then just slow down or make it faster or quicker. But just for the sake of like making this easing more like easy to see, we can just plot that thing, and you can see how this formula of the easing looks like. Cool. Whew, I hope this clears it up a bit, but basically all of this works just to say that easing is going to be the one telling you how fast your animation is playing. But let's look at how this looks like in code. Same with AnimationSpec, the only thing you need to do is, giving an animation, you just need to pass your easing parameter. Easy, right? And same as AnimationSpec, you don't need to create your own, because there are already several out of the box, like the ones I was exemplifying. But of course, since this is just a simple formula, you can basically grab these easings and easily change your animation by creating your own formula and creating your own custom easings. And with this, I'm going to actually leave easing behind because regular easings are boring. So let's jump into customization number 3, custom easings. Now, when talking about custom easings, everything still applies. This is still going to be talking about the speed of how your animation is going to be played. But the difference is that you're going to be providing your own formula. Whenever you delve into custom easings, you're going to actually have 2 options on how to create them. Option number 1 is to play with the cubic bezier easing out-of-the-box function that you have, which is going to let you create some wavy, some curves in there. Or option number 2, the fun one, is to just create your own custom easing from scratch. And don't worry, even if it looks daunting, it's actually quite easy. The only thing you need to do, since it's just a straightforward function, is grab your favorite function, like a sine wave, and just stamp it into an easing. And by doing that, as you can see, it's just a one-liner. This is just copy-paste from my repository. You just create a random different easing that changes totally the behavior and how this animation is traversed. And don't worry if you're having some troubles on how to get inspiration for these weird formulas. There's a lot of it to be get by the easing.net page. But again, going back to our visualizers, I am trying not to forget about them. The only thing we need to do is basically grab our custom easings, paste them inside our twin animations, and that's it. And in order to make this a bit more funner, there's no way of just like getting satisfied with one thing, right? We can just paste them all together. And that's it. I think that's it with our cooler Easter visualizer. But now that we're talking about custom easings, you may be wondering, hey, now that we're delving into customization and creating our formulas, what about a custom animation spec, right? Well, don't worry, the answer is yes, of course, you can do your own. So let's just jump into customization number 4, custom animation spec. Because of course, nothing is stopping you from creating your own. And in order to create them, you again have 2 options. Option number 1 is to use keyframes. As I mentioned before, this is kind of like a super flexible animation spec that is going to let you define specific keyframes you want to hit. It's super flexible, and for most cases, this is the only thing you need, but we're not going to go with the simple, easy way. We're going to go with option number 2, which is create your custom animation spec from scratch. And in order to do that, let's just go with my favorite formula that if you haven't noticed, let's just create a sine animation spec. This is going to be a 2D animation spec that instead of traversing in a line, is going to follow a wavy path until it reaches its end position. So let's start seeing some code with this. In order to start, we again need to go back to our interface, which as we saw is basically just a container for our vectorized animation spec. So I guess we should start with that sine vectorized animation spec first. And since I already mentioned that this is going to be a 2D animation spec, we need to start creating our myVectorSpec. Again, naming is hard. And instead of returning use a vector, we're going to return an animation vector 2D. Because I said I was going to work 2D. Don't worry, there are a lot of them. You don't need to start with this. Once that we have this, let's just now go implementing each of the functions one by one. And let's just start with the bottom. Let's talk about duration. In order to define the duration of my custom animation spec, we can just take an example of the other animation specs that we saw, and let's say that we just pass it as a parameter, right? Why should I complicate this? Great, that's it. That's 1/4 of it done. Let's jump into the next function we need to implement, the velocity from nanos. Now this velocity is where easing would come in, and basically we'll be reporting how you can change like the different velocity of the animation, of playing different parts faster, different parts slower. But for the sake of simplicity, let's say we are not going to change our animation velocity and we're going to keep a constant speed. If that's the case, you can just basically provide an vector vector 2D with 0, 0, and that's it. Great. That's half the way, right? So let's jump into our third function, that is get value from nanos. Sadly, for this one, it's not going to be as simple as the other two, because in here is where we are actually going to define the path my AnimationSpec is going to take. So this is where all this sign formula is going to come into play. And it will look like this. Don't worry, we're going to break it part by part. The first thing we're going to do is we're going to grab the initial point where my initial value is going to start. After that, we're going to get then position of it. Once we have that, we're just going to calculate the general difference between them so we get the values we're going to need to advance in X and Y. Everybody's still with me, right? Great. Now that we have this, we're going to create the distance between them, which in this case is pretty simple, it's just a triangle thing. And once we have that, don't worry, we're just using this for like define what is the direction this animation is taking. And once we have this, we have the general plot or where our ball is going to start and where our ball is going to end, right? We have the total distance we need to traverse. Now that we have that, we're going to actually get the progress to see in which point of this distance we have already advanced. Now that we have this thing, this is where our function is going to come into play. Because we don't want this to advance in a line, we're going to use the sign function in order to identify how much we need to move our ball in this path. Nice. Now that we have this change, we just need to put it inside an animation vector 2D, and that's it. That's all the things we need to do. As you saw, it looked a bit daunting, but it actually isn't. The only thing I am doing is plotting a formula that is going to tell me that at a specific point where I am going to be, and it's just a 2D formula, right? It's X and Y and coordinates as you saw before. You can basically replace this off the chain with your favorite formula, like a spiral or a cosine if you're one of those, and just do whatever, right? But going back to our vectorized animation spec, we have our three functions done. The only thing that I'm missing is to define that this is not an infinite vectorized animation spec, even if I would love to, let's say it's not. And with all of this done, we are done with our vectorized animation spec. As you saw, most of these things were a one-liner. The only thing that is interesting was our value from nanos, which is where most of the bulk of the logic is going to be. Going back to our sign animation spec, the only thing we need to do is create our sign animation spec and return our vector spec. And that's it. We're done with our custom animation spec. In order to use this, the only thing we need to do is go back to our previous animation and pass the value as any other animation spec that we did. Now there's a small difference here. Before we're using float, which is a 1D vector basically. So in order to use my 2D one, we need to change the values and use offset, which is basically a 2D property. Offset basically just contains X and Y, and it's a nice way to like plot things in the screen. But that's it. Once that we have this change, if we run it, we already have a sign animation spec. And that's it for this. So let's go back to our visualizers and let's start placing everything together. Let's just grab the sign, let's just grab the easings, let's just add even more easings in there, and because why not, we can start playing around with some sizing and with some colors as we saw before to make it even more interesting, and because why not, we can make it cheap. And for now, that's it. So, thank you.